name's Andrew Corbett, and I am the developer of the Mine Simulator, which has been developed in conjunction with the mining industry. This is the first video in a series of videos. In this video we're going to detail the background of the company called Mine Port Simulation Services and the dynamic simulation tool called the Mine Simulator. The reason for this video is to detail the reason why TMS has been developed over the last 10 years. The detail the benefits of using TMS, which are mainly the reduction in time and cost to use dynamic simulation modelling and analysis in the mining industry. List some of the previous applications of TMS in the mining industry, and list some of the previous and current users of TMS. As I said, this is the first video in a series, and this video will be followed by other videos that will detail more functionality of TMS as applied to simulating a mining operation, simulating a port operation, or simulating a rail operation. It should be noted that TMS will simulate a mine and a port, or a mine and a rail, or any combination thereof. I'll just discuss briefly about Mine and Port Simulation Services. Mine and Port Simulation Service was established in 2008 by myself. I have roughly about 38 years experience in the mining and marine industries and about 15 years experience in dynamic simulation. I've worked in a number of mines around the world, mainly in the area of mine engineering, ranging from short-term, long-term planning, survey, production control, been a heavy equipment operator, operating haul trucks and loaders, and worked on all road maintenance crews, etc. And I was also been involved in lots and lots of projects for the mine industry over those years. What I believe I've done, I've developed what I believe is kind of a new concept. Well, it was definitely a new concept 10 years ago. It may not be today, but 10 years ago when I started developing TMS, it was a new concept. And the idea of this concept was to greatly reduce the cost and the time making dynamic simulation and analysis to more companies and projects. And that was the reason I started Mine Simulation Service, Mine and Port Simulation Services. And that was to continue to develop TMS over the years. So it was established just to divide process improvement analysis via dynamic simulation to the mining and marine industry, not to just the big players, but to the little players as well. And I've focused in on these areas because even though I know about dynamic simulation, I'm always worked in the mining industry, and I believe systems that are developed by people within the industry are far superior than systems developed by people outside the industry, because that people just outside the industry don't understand the little details that are important to us in the mining industry. So that's why I could have developed some system for some other industry, but these are the ones I've been working in. This is all for over 38 years, and this is the industry I know. So just a quick thing about what is dynamic simulation. It's virtually just a replication of a process in a computer. And the advantage of this is that you bring in a time component, so things interact on a time clock type thing, and you can introduce all the interactions between the equipment, and you can introduce variability and breakdowns and stuff like that. The reason why we do it is that we want to look at how the process may change without impacting on production or introducing safety risks. So we don't want to say, well, let's look at doing something to our process and then find out it doesn't work, and then we've lost production, which we'll never pick up again. So we use dynamic simulation as one of the better tools, because it takes in the whole range of aspects of the mining operation, or port or rail, to do this type of analysis. And over the years I've found out a good simulation doesn't use operational data to control it. The simulation should be able to just use common sense logic, or the natural physical interactions between mobile equipment and the environment they work in, and the fixed plant and all that sort of stuff. And this also enables the simulation to generate interactions what we would not normally consider. So the simulation has to be self-controlling and looking after itself. It shouldn't have to have lots and lots of data to control it. And like I said, the main reason we do this, we want to reduce the risk in our decision-making process, whether that decision is to put another truck on or take a truck off the operation to dredge the channel to a certain depth in a shipping operation or whatever it may be. The whole idea is to reduce the risk in making these decisions. 10 years ago, I looked at what a lot of people were using dynamic simulation at the time, and there was like what I call the classical approach to doing dynamic simulation analysis. And because the classical approach, it required a lot of time and cost to develop these types of simulation models. And that's why back then they were only applied to large capital spend projects that, projects that were going to run for a year or more and had lots of money to spend and all this sort of stuff. So in this classical approach, the first thing people used to do is the purpose of the process analysis is defined. Why are we doing this analysis? What are we trying to get out of it? This plus the timing cost constraints posed on doing simulation analysis is one of the biggest reasons why simulation analysis at the time had a bit of a bad name. And it's because people used to define what we're going to use the simulation for, and therefore the simulation was designed and created around that reason. And therefore it wasn't a full system that could handle other processes or changes to it, really, because it was really just defined to answer a particular question. Therefore the flexibility wasn't built into it because they didn't want to spend the money all the time putting that sort of flexibility into it. The second stage is usually to document the process and then describe it to the internal or external simulation consultant, which is at that particular time was a specialist. And then the consultant developed a simulation model and he verified it, hopefully, and then it was validated, usually against an existing operation if on the brownfield, or a similar process if it's a greenfield type project, and then the simulation was used to analyse the process. The simulation system TMS I've developed is kind of eliminated step 3. We don't develop a simulation model. We have a TMS which has been applied, a simulation system that has been applied to lots of operations around the world and has the functionality and flexibility to do most of the things that the purpose of this process analysis is defined to do. The TMS will already do that, and not only that, it will do a hell of a lot more. So it makes it much more flexible. And then because we don't develop a simulation, straight away we reduce the cost of the whole applying dynamic simulation to a project, and we also reduce the time. Both means that when you use TMS, you can get virtually straight in to do the analysis side of things, knowing also that the simulation is being validated against, or TMS is being validated against a lot of operations around the world. When I did this initial analysis back 10 years ago of current projects using dynamic simulation as an analysis tool, these are some of the negative things people told me about simulation analysis. Simulation models are expensive to implement. At that particular time, yes, that is true, and it's still true today. To do a good simulation takes a lot of time and it takes a lot of cost. So the project has to bear these costs to generate a tool they can use for that particular project. Also consumes vast amounts of operational data, and also this consumes a large amount of time from operational staff. This was more of an issue 10 years ago, before a lot of the mining operations are automatically generating lots and lots of operational data, and they have it at their fingertips. In fact, a lot of mining operations don't know what to do with all the data they generate. So it's not so much of a problem, but as I pointed out before, the simulation shouldn't be using large amounts of operational data. It should be, I take operational data and I compare the output of the simulation to what the operational data says in my validation process, but I don't actually use it within the simulation. Simulation can be manipulated to generate the required outcome. This is true. In the old systems, they used to be able to do that. I've overcome that. It's not an issue. Simulation has a finite life, usually the current project. This is true. Because of it costs so much to develop these simulation models, they were quite designed around that particular project. And then for when you want to use to say, oh, well, let's run it now. Now we've got the mine operating, let's run it with a different type of truck. The simulation couldn't do it without actually changing the simulation. A lot of the times, to keep the cost down in developing the simulation, a lot of the stuff inside of the simulation were hardwired to that particular project. They're just not flexible. Back then, simulation also required special skills. Mainly, yes, to develop a simulation, you had to know some sort of simulation language or what have you. I've overcome that by developing a simulation tool that anybody can use virtually. Just if you've got Excel spreadsheet skills, you can use TMS. Simulation restricted to large capital spend projects. This is true back in the old days because it costs so much to develop it. I've overcome that problem in TMS in that it's just a simulation tool being applied to all mines and rails and ports around the world. So you don't have to spend the money to use simulation dynamic TMS. So TMS can be applied to all projects, whether they're large or small, just to increase the confidence in the analysis. Simulation analysis is good for sizing stockpiles, bins, etc. That's all. That was true back in the old days. Not so much nowadays because we've got more detailed simulations that cover everything. TMS covers everything. So you can look at things like operator skill level and all these sorts of things to work out what impact it has on your production. Simulation is only a model. All models are inherently wrong. I agree with that. TMS, as I'll explain later on, has gone out of my way to make sure there's no models within the simulation as such. So I don't call TMS a simulation model. TMS is a simulation. And I'll go in a bit more detail because this is an important point. Simulation detail, functionality and lifestyle is restricted by project cost and limitation. This is true in the old days, not anymore. TMS has got all the functionality you would want. It includes all the functionality from lots of mines and ports around the world. So when I run TMS, I know I've got at my disposal all the functionality that any new project may want to look at, whether it's different types of shift changes, running different types of graders for haul road maintenance or whatever it may be. The functionality within TMS is already there. So the cost to implement it, to use it, is much reduced compared to the old days. Also, when I did this initial review 10 years ago, the one thing that kept coming up was that people liked the analysis of simulation because it brought the time component in and it included all the interactions between equipment if it's a good simulation. So they felt that even though it cost a lot, the analysis generally gave them a higher degree of confidence that what they were proposing was going to actually work when it was commissioned. And also a good simulation, it highlights interactions that we miss by conventional analysis. I.e., you can use a simulation to find the low-hanging fruit, but a simulation will also enable you to pick the fruit you can't see, and that's the most important thing. One of my biggest benefit I get out of doing this work is when I present the results and manager operations have what I call a no shit moment. That is, they say, Andy, I understand what you're saying. I understand why you're making this recommendation, and it's interesting. I never thought of that before. They just don't. The simulation enables you to see interactions that you don't normally see. Even when you look at the operation, physically look at the operation or analyse the data, sometimes you just don't see these interactions. And some of these interactions only occur for a certain period. They may not occur for the whole year. They may only occur during the wet season, or they may only occur for a month or something. But if you can see that interaction, what impact that's having on your production, then you can maybe do something about it. And also, it also highlights the good things. If you have a good month and you're running the same trucks and loaders and you have a good month, you can look at the simulation and say, why did I have a good month? Was it because I had good truck availability or loader availability or whatever it may be? And it gives you a bit of a direction to look at, to try and turn your bad months into good months or what have you. So what I've done, I've created a new approach to simulation analysis. This new approach to simulation analysis is mainly to come up the issues I just mentioned previously. And it also to utilise my previous experience and has to design a simulation tool for the mine industry, and I've just called it the Mine Simulator. Keep it simple. And it was originally released in September 2008. But this version was mainly just a simple truck loader type operation. Didn't have enormous amounts of bells and whistles. It had some, but over the years, the detail has been added to the Mine Simulator. I've made it reasonably flexible by using an Excel spreadsheet front end. Every mining engineer knows Excel like the back of their hand. And what you virtually do is you populate this spreadsheet with your mine design, your haul road, your operational data, and everything you want that impacts on your operation. And then TMS, which is being developed in Arena, reads that spreadsheet and simulates whatever's in that spreadsheet. So as you can tell, TMS, or the Arena version, TMS, doesn't have any hard wiring in it. It can't have any hard wiring in it because it's designed to simulate whatever's in the spreadsheet. And that spreadsheet could be a mine. It could be a mine and a port. It could be a rail and a port. It could be several mines and all sorts of things. So the TMS is the engine that does the work of the simulation, but as far as us human beings, we're more interested in the Excel spreadsheet, because in that we have all our inputs and we also have all the outputs, the reporting from the simulation in that spreadsheet. As I stated before, TMS was originally released in September 2008. In the last 10 years, it has been successfully applied to over 33 projects around the world, and in those particular projects, it's been applied multiple times for multiple different projects within that operation. And for each of these projects, TMS has been verified. That means TMS operates the same as the mine does. It sends the trucks to the right loading units. The plant operates the same. It just, how it operates and things interact is the same. It's being validated. That means I usually run the previous year's operation through TMS and look at what TMS says they should have produced and what they actually produced. And generally, TMS will report within less than 1% the actual production. It will report less than 1% the actual production of individual digging units and trucks. It report less than 1% the availability of equipment and stuff like that. Remembering that availabilities are not input into the simulation, they're an output. So it gives you confidence that the simulation is working well. And remember, every project that's being worked on, it gets validated against if it's a brownfield operation. And it's been enhanced. So over the last 10 years, not so much nowadays, but early on, every operation you go to, they did things slightly different. The way they did their shift change may be slightly different. Some mines just do a shift change where the trucks pull up and then the other guys go out and off you go. Others do a shift change or a crib break, Some mines, the trucks go in, it's off the road for half an hour while the guy has a crib break. Other mines use a relief crew system where a third of the trucks come in because they've got, a lot of the ladies at the mine operate the trucks for a couple of hours while the trucks swap out during crib break. Well, these sorts of things. Different operations do things differently. But when a mine does something different, it goes into TMS, but it doesn't go into TMS the way they do it. It's put into TMS so it's flexible, so that TMS can do what they do and also do additional things based on what they were doing. So it makes it more flexible for that particular operations as well. So there's a lot of history in TMS, and there's a lot of functionality in TMS, and like recent years there's been reduced amount of enhancement to TMS because it's been applied to so many open pits and stuff and ports and stuff. It's virtually got most things covered. This result in that TMS is a pretty mature system, and it's backed by a database of operational data that TMS will be quickly applied to any mining, rail and port operation. The operational data is really important when it comes to applying TMS to a greenfield project, i.e. something they're thinking of building. And it enables TMS to be applied right up the front at the order of magnitude stage, because some people say, well, why do you want to apply a simulation, which, we're doing an order of magnitude study on a mine or something. Why do we want to worry about how we're going to do shift change? Well, because TMS has all the different types of shift changes and the different ways of doing it. I can just specify this is like a standard way people do shift change. So for an order of magnitude study, that's fine. This is how we'll do shift change, and it gives you a lot more confidence when you're doing your order of magnitude studies of looking at the different scenarios and which one comes out the best. And because of this, because we can get the simulation up and running really quickly, may only take a couple of days in fact, it reduces the cost and time over conventional methods of doing this type of analysis. But more importantly, it increases your confidence in the results because TMS has been applied for so long. Right, some other advantages of TMS, or this new approach to doing this. Like I said, there's no time and cost restrictions. I keep harping on about that, but that's really important. And that's why I often get, when I do a proposal, sometimes I get called in and asked why I'm so cheap. And it's because I don't have to develop a simulation. I don't have to spend 2 months developing a simulation. I've got something that's going to operate straight away. And not only that, I've got the flexibility and stuff to emulate the mining, rail and port processes in detail. And not only that, I've got the flexibility already there to look at different things. I can look at how they do shift change at Antamina. I could apply that same sort of logic at Mount Tom Price or something like that. No issues. So that's one of the advantages of having a simulation tool, as opposed to, like some people say, we'll build a simulation model especially for you. Like, that's a good thing. To me, that's a bad thing. Having a brand new simulation, how confident you are that it's doing the right thing can be a lot of time. Maybe that's part why they're so expensive. But TMS, you don't really have to do that. You don't have to worry about that. There's a lot of confidence in the results it generates. Like I said, the functionality for many operations are already in TMS. So, and as time's gone by, when we're slowly not adding as much functionality to TMS because we go to a new operation, how they do things is already in TMS. So we don't have to do any development there. TMS, the main reason, one of the design criteria of TMS is that to come as close as possible to the physical operation of the mining process. And to do that, we don't allow models to be included in the simulation. And I keep talking about this simulation models and how they're a bad thing. And I'll just go through that in a bit more detail in a minute. So TMS is based on the physicals. It's all about the common sense interaction between mobile equipment and fixed plant, and just physically you cannot dump a truck load into a hopper if the hopper's full. Just common sense stuff. And that's how TMS is virtually designed around. So it's It's got just common sense stuff in there. So it's it's not saying anything about a particular operation. It's just common sense stuff. You just can't do it. You know, just that's what TMS is based on. The philosophy behind it is just exactly that. The other thing I like about TMS is that all the mobile equipment is in their own little special Excel spreadsheet. So you can have an Excel spreadsheet for a Cat 7-9 whatever truck, and it has its rimble curves, its retard curves, the planned maintenance, regular and major maintenance. So there's a simulation tracks SMU hours or operating hours on each piece of equipment. You know, the servicing data on the equipment, the breakdown data, TK, pH, fuel consumption, all these sorts of things are in these little spreadsheets. And so you can have as many of these as you want for different types of equipment, and you can take a particular type of Cat truck or whatever, or Komatsu, and actually change some of these things if you want to see what impact that has on your operation. Once again, TMS is designed to simulate any mining operation, and therefore only it requires limited operation data from the mine to actually simulate it. Things like truck availabilities and load times are all generated by the simulation, so they're not inputs, they're actually outputs. So we use them to validate the simulation against an operational mine. The only things, operational data we put in there are things that the simulation just no way in the world it can determine by itself. Things like some mines have, you know, all stop, one stop, all stop, you know, delays, whatever they may be. Some other operational delays, standby and operational delays that are just human generated by that particular operation. And yeah, I won't go into detail because some mines have a lot of them, and that's one area you can easily pick up some gains by just their previous practices, which no one's questioned before. So only limited operational data is used within TMS, and therefore, because of that, TMS cannot be manipulated to achieve a desired outcome. There's not much you can actually change to make a thing happen what you want. And having the mine design outside the simulation allows for, you know, open pit, underground combination thereof, and all the rest of it and rails and ports to be simulated by the one system. So it's easy because it's not hardwired in the simulation. You can change the haul road design layout in the spreadsheet and then simulate it, no problems whatsoever. So all those sorts of things are flexible. Everything's flexible virtually in TMS. The other thing is having a single simulation increases your confidence in the results. It's been applied to so many operations around the world for over such a long period, and it's been verified and validated. I know in TMS a haul truck is going to behave correctly because so many times I've put GPS trackers in trucks and compared their haul cycle with what the simulation is generating, and it's usually pretty well spot on. And not only, it's not just every haul cycle is slightly different, and that shows up in the simulation as well. So there's lots of, you know, the nuts and bolts of this type of work is, you know, valid in the simulation from day up. There's no issues about it. TMS is holistic. It covers from mine face. It includes waste. It includes ore. It includes all your truck dumps. It includes all your fixed plant. It includes your processing plants. It includes all your shift changes, how you run mining campaigns, your shipping, and your wind, and all these sorts of things are included in TMS already. And one of the advantages of TMS, I've found out over the years that, you know, it can be configured to use in, has been used in, like order of magnitude study, pre-feasibility study, feasibility studies, and analysis of existing operations. Previously, people doing order of magnitude studies, for example, may shy away from using simulation analysis for several reasons. The cost to do it, and also, you know, the amount of information you need to do it in the old days. Nowadays with TMS, you don't need all that information. You know, some people say, why use simulation analysis for an order of magnitude study? I don't want to, at this stage, define the shift change or how they're going to do crib breaks or whatever. You know, it's an order of magnitude study. But because TMS already has the history about those sorts of things, it's easy just to say, well, industry standard, this is the way most people do shift change. So for an order of magnitude study, well, this is how we'll do shift change. And as the study progresses through to feasibility stage, then you can start, well, this is a way we're doing shift change. Let's look at, what impact it may have on this particular operation if we do shift change slightly differently. And so the same simulation, same spreadsheet flows through from the order of magnitude study right through to when you're doing the analysis of the existing operation. So the money you do spend, any money you do spend on TMS, it's never lost. The system will continually work right through all your studies too when you analyse your existing operations. And TMS has been used in different projects. The function of TMS has been expanded. We've gone over this a few times. So it's led, eventually we ended up with a tool that is truly verified and validated, and also a tool that greatly reduces the cost to implementing it. And it's a tool developed just for the mining industry, ports and rails. Now, I'll just go back. I've mentioned a few things about simulation modelling and what I call pure simulation. Now, in the old days, due to project time and cost constraints, the classical approach to simulation generated a simulation model or models. And what I call a model is that because they wanted to get the simulation done as cheaply and quickly as possible, for an example of a trucking operation, they may have been just using one type of truck, and one type of loading tool, whatever it may be. So they may have just said, well, give us the historic load time for a truck. And so they may just said in the simulation, say, each truck gets loaded in 5.6 minutes. So, well, they may put a distribution of load times from 5 minutes to 6.8 minutes or something like that. But that load time that's what I consider to be a model. It's something that represents a much more complicated process being simplified into a model. And because TMS has not been any time or cost constraints placed on it, it's moved towards what I call more of a pure simulation. The pure simulation is just something I use. There's no industry thing about that. But what it does, you don't put in truck load times. The simulation calculates truck load times using the physical interaction between the truck and the loading unit, the face height, the operator's skill level, their material attributes, and all these sorts of things to actually generate a load time. And that load time may vary. The advantage of doing like TMS is that the simulation, the previous one up here, if you had load times, you can only use this simulation for this type of truck and this type of loader. If you want to use this simulation, say let's put a truck with a lighter tray in, or a bigger tray, or a different type of truck, then you're going to have to get this information about load times for that particular truck and the type of loading unit you have. With TMS, you just say, well, this is a different type of truck, therefore the simulation will automatically readjust the load time because this truck takes on a bigger payload or whatever it is, therefore there's maybe more passes to loading that truck, if you're running a different mine plan, and this particular mine plan, if it's a bauxite mine, say, the mine face is getting slightly thinner, therefore the fill factor on the loading units is slightly less, therefore it may take longer to load the truck or something. So the advantage of doing it like this without any models is that the simulation is much more flexible. You can automatically handle changes to the process and report on those relationships, which would not, a classical simulation would find. And it gives you more confidence in what it's doing, is doing the right thing. This is just very generic. Back in the old days, if you want to do a simulation model of a mining operations, reasonably, a big open pit or something, take at least 2 months to develop the simulation and cost $80,000 or thereabouts. If you want to add more detail on the simulation, it take longer, cost more, and I've seen people spend 12 months and $1 million developing a simulation of something. trying to get the detail in there and all the rest of it, and not the flexibility. It's still being quite specific for that operation, and big dollars and lots of time. Whereas TMS takes 3 to 4 weeks. Actually, can take a lot less than that, and maybe $20,000 or less than that to actually generate a really pure simulation, and a simulation that really emulates that operation. And not only that, is really, really flexible. You can really use it to look at a lot of different things. Like I did a hackathon the other day down in Sydney in Australia, where it was sponsored by a gold mine, and one of my tasks for the particular group I was in was to verify the savings on a improvement idea they had for that particular gold mine. And I actually had that simulation of that gold mine operational the first night we were there. So it only took a day. It wasn't you could say, pure simulation, because they didn't provide us all the data which we really wanted, because it was, we hadn't signed any confidentiality agreements and all the rest of it, so they only kind of got this high level data. So, but the simulation still worked quite well, and we were able to use it to generate the benefit of the change to their particular process. So that's one of the advantages, and so this keeps the cost down. Okay. Now, I'm just going to go through the mine simulator in a little bit more detail, just to give you an overview of TMS. There's a high-level overview of TMS, the mine simulator. As I said before, TMS consists of an Excel spreadsheet in which you put all your inputs. You put in your haul road design, your shipping channels, your rail network, which trucks you want to use, how you want to operate shift change, all these sorts of factors that go into the Excel spreadsheet. And then there's a TMS which I've developed in Arena. This version of TMS in Arena reads whatever's in the Excel spreadsheet and simulates that. So if you have a mine in here, TMS in Arena simulates a mine. If you just have a mine and a port, TMS simulates a mine and a port. Now, I've used Arena mainly because it's a well-accepted dynamic simulation language in the mining industry. But my preference for Arena is that I'm able to go down to a programming type language which enables me to generate inputs or generates functionality within TMS that I could not do otherwise. Arena was originally developed for the manufacturing industry. It's called discrete dynamic simulation. The discrete side was designed to do for discrete elements, things like making fridges, washing machines, cars, etc. in the manufacturing industry. In the mining industry, we do have discrete elements like trucks and loaders and ships and trains and other things. But we also do a lot of bulk handling, materials handling. So to handle that in Arena, I've developed my own constructs, things like a conveyor. In TMS, when you put material onto a conveyor, you put it on at a particular rate, and also the material has up to 20 sort of grade attributes, whether it's silica content, gold, hardness, yield, all those sorts of things you can have in there as part of the material which is going onto the conveyor. Then as you feed material onto the conveyor, the rate may stay constant. You may be feeding it at 2,500 tonnes per hour, or because of the parts of the process before the conveyor, the rate may slowly change from 2,500 tonnes per hour to 900 tonnes per hour. That gradual change will be seen along the length of the conveyor in TMS. It knows exactly the profile of the material along the whole length of the conveyor as the rate of the material which goes onto the conveyor changes. Not only that, TMS also knows how the grade attributes of the material in there may change as material goes onto the conveyor. An example is you dump a truck in the truck dump which has a 10% whatever, and then the next truck has 5%. Well, when that first bit of truckloads may go onto the conveyor. It may start off at 10% or whatever material attribute, and then as the material, the 5% material gets mixed up, the grade on the material going onto the conveyor or the feeder will slowly change, and eventually at the end it may be a small proportion of 5% material. The TMS knows this, and it tracks the material through along the conveyors to handle the bulk materials handling. The TMS also knows this through other things like truck dumps, run-of-mine stockpiles, etc. But that's the reason I use TMS, because I could build these sorts of constructs to make TMS a much more precise and accurate simulation system. So once you generate your input spreadsheets and you run it through TMS, TMS generates a whole pile of standard reports which you have control over, how you want them developed, what time period and all this sort of stuff. And then the Excel spreadsheet you used as your inputs also reads in the outputs from TMS. So you end up with a spreadsheet that has all your inputs and all your outputs. So you can come back to this spreadsheet 6 months' time and you know how it was done. You know all the inputs and you also know all the results. So in a particular project, we talk about a very simple one, just talking a small operation with 5 trucks in it. You could run TMS with 5 trucks, run it through, set up your spreadsheet with 5 trucks, run it through TMS, and then save the results with 5 trucks. Then you can take a copy of this spreadsheet, call it something else, and put 6 trucks in it, run it through TMS, and then save all your inputs. So then you end up with 2 spreadsheets, one with your mine running with 5 trucks, one with your mine running with 6 trucks. And then you can keep repeating that until you end up with a whole pile of spreadsheets with 5, 6, 7, 8, 9, 10, 11, 12, whatever trucks. Then once you've finished doing all your runs for your different number of trucks, then you can open up another spreadsheet and interrogate these spreadsheets. So you can generate charts saying tons versus number of trucks in the fleet, or throughput versus tons and number of fleet. Not only that, because the Excel spreadsheet reports have all the activity-based reporting for each of your trucks, you can start looking at, well, not only does my tons go up, or my tons may go up to a certain level and I keep adding trucks and it doesn't make any difference to my throughput, you can start looking at, do charts of time trucks are waiting at the loader, time trucks are waiting at the dump, etc. And you may find that as I increase my trucks up to a certain level, my trucks are losing hours by spending too much time waiting at the truck dump. So from there you can say, well, maybe I should look at how I handle my run-of-mine, reclaim, dumping and processes. And you can look at changing how you do send trucks to the truck dump, how you send trucks to run-of-mine, when you reclaim from run-of-mine, and you may be able, just by changing the process, increase the number of the tons you get through for a particular truck fleet. And so that's a very simple way to just do some simple analysis using TMS as such. So that's very simple stuff, but that's kind of an idea of what you can do. Also, as part of TMS, I've mentioned before, you have all these specification files for each of your piece of mobile equipment. So you may have 5 or 6 specification files for trucks, each representing a different truck type. So when you have all these specification files, when you have them in your working directory on your computer, this TMS spreadsheet has access to them, and then you can just put on a pull down menu, just pull down which trucks you want to have in your fleet. So that's a benefit. Now, just go through how TMS has been applied over the last 10 years. This is just some of the applications, but we've done a lot of work on production analysis, both open pit and underground, i.e. how many tons we're going to get through the system. Do we need more trucks? How do we change? What parameters can we change so that we get more tons through the system, or how can we reduce the truck? How can you get a truck off the road? It comes along with a lot of truck and digger fleet analysis, size analysis work, a lot of truck specification analysis, like reducing the tray weight. Did one particular project where the mine said, we're going to reduce the tray rate by putting a lot of trays on and increase the payload by 5 tons, and this is what we believe will be the benefit. I actually ran it through the simulation. I did get a benefit, but not as big as what the mine thought they were going to get using static analysis, and I could the simulation quickly highlighted that the issue was that trucks were waiting that tiny little bit longer when they were queued at the truck dump. Because the previous truck was dumping a slightly more tonnes, it took longer for the feeder, which was still running at the same rate, to get rid of those extra tonnes. Therefore, the next truck was waiting just that little bit longer. It's all these times after tens of thousands of truckloads during the year. Those little times added up to an increase in the time trucks were spending at the truck dump, something they hadn't considered in their static analysis. That's one of the advantages of dynamic simulation analysis. I've done a lot of mixed fleet analysis. Not such a good idea in some operations, but there is some benefits. Done a lot of mine procedure analysis, how to do hot seat changes, shift changes, when to have meetings, whether we should use a relief crew during crib breaks and all these sorts of things. One of the advantages of TMS that's been applied to so many different mines, it has all the functionality. You can run all these different types of crib change, how you want to run your crib changes. So you can easily run crib changes if from a different mine at your mine, just to see what impact it has. Done a lot of grade control and stockpile analysis over the years. Things like this, even considered different types of stockpile stacking, cone or chevron, etc., and the impact that has on shipping grades. As I said, TMS tracks your grade right through from your mine face right through your whole system onto your ships if you want to. So you can see how these different types of stockpile stacking may have an impact. As you know, chevron stacking gives you most likely gives you a better blend, because you're slowly spreading your grades right across your mine, your stockpiles. But in some instances, actually cone stacking is better, depending on how many stockpiles you've got and the size of your ships and all that sort of stuff. There's a relationship going on there. Done a fair bit of haul road analysis, just looking at the layout, whether making intersections, changing intersection layouts and stuff like that, how that has an impact on production. Some of the bigger mines done quite a bit of haul road analysis. The simulation has some reporting there that tells you some of where the hot spots are, and there's lots of trucks, and often you can get around it by just changing your haul road layout. Mine plan analysis. Some mines I run next year's production through, just to give people a bit of a feeling of probability that they're going to meet tons production next year, and if not, what some of the things are maybe they should be targeting, like it might be truck availability or something. They should be targeting that next year to get the throughput they require. Done a bit of analysis on run-of-mine stockpiles. This is one thing a lot of people don't think about, which is over the years I've found to be very important. Main thing is the location of your run-of-mine stockpiles relative to your truck dump, and how many trucks you're using for reclaim. This can have an impact. You don't want your run-of-mine stockpiles so close that when your run-of-mine trucks end up queuing and etc. You want it just this nice distance away from your truck dump. So that's when the trucks are running to run-of-mine, the haul distance, the cycle time is slightly less than if you have the run-of-mine stockpile right beside your truck dump. Done autonomous truck fleet analysis, which is quite simple. When you can do everything else, it's quite easy to take an operator out of the truck and reduce some of the delays and the impact thereof. Done a lot of fixed plant analysis, looking at conveyor sizes and rates, especially in underground mines, and also looking at the fixed plant maintenance, how that impacts, especially when you have plant maintenance on your Benny plants, or as well as on your ship loaders and all that sort of stuff. Done a lot of analysis, truck decline versus conveyor inclines and order of magnitude studies, etc. Done a lot of work on channel ports, channel depth analysis, siltation, trying to work out port capacity, and how ship loaders discharges work, and how increasing their rate or whatever it may be, or reducing some of the delays associated with them, how that impacts on port throughput. Done a fair bit of work on mining campaign analysis, how the mine should run whether it's a pull campaign or a push campaign, depending on how you do your campaigns, i.e. do you run them on a time base, run this material for 3 days and this other material for 4 days a week, or do you run it for X amount of tonnes this campaign, do 20,000 tonnes, and this other campaign you do 40,000 tonnes, or you run it that when the level on a particular product stockpile gets below a certain level, you actually trigger a mining campaign for that type of material. So this is one way in the simulation you can really run it at a push system or a pull system. Done a fair bit of work on graders and water carts. Simulation monitors haul road usage and etc. So it knows when to dispatch graders and water carts and stuff. So once again, this is one thing: you don't want to over maintain your roads, but you don't want to under maintain them such that your rolling resistance starts to go up, etc. So done a lot of work with barge and transshipping, looking at bringing barges down rivers and changing them over to the material, transshipping it or into ocean-going barges, then out to export vessels, etc. Done some road train analysis, but not too much. It's not one of the things I've done a lot on, but done a few mines. Done a lot of long-haul trucking versus rail versus overland conveyor analysis for order of magnitude studies. Fair bit of material blending analysis, mainly for the coal industry, and in-pit crushing analysis, something we all do for the larger mining operations, as well as lots of other things that simulation is capable of doing because it's so detailed. Now, where has it been applied? Some of the mines it's been applied. Gove Port over in Australia, looking at improvements to the mine. Whipper Mine, rail and port, whole pile of different projects. I can't go into too much detail because I have confidentiality agreements with all these people, so I'm not going to mention too much detail. Mount Arthur coal mine, that's a very complicated mine as far as blending of coals, etc. Antamina copper zinc mine over in Peru, just looking at expansions, congestions, in-pit crushing, etc. Kennecott Utah Copper, they can't use the system in-house for a while. Riversdale Mining, that's barging coal down the Mozambique River before Rio Tinto took them over. Port Alfred, just looking at all different aspects of the Port Alfred operation over in Canada. Panamonica Iron Ore Mine, just a bit of work there. Port Kamsar in New Guinea, once again looking at improving throughputs. Teddy Mine, a number of little odd jobs for them over the years. Moolarben Coal, a number of, once again, a whole pile of different, looking at new operations, expanding the operations. Mount Tom Price, once again, I think that was one of the projects I did when I was looking at reducing the size of the weight of the trays on the back of the trucks. Hunter Valley operations, a whole pile of improvement ideas. Brockman and the Melody, once again. Port of Holyhead was just once again trying to bring in new material into that port. Mount Thorley, Wackworth, that was a whole pile of Six Sigma ideas which we ran through the simulator, and actually 2 of them I think showed reasonable sort of promise. The rest of them weren't worth doing, which was one of the benefits of the simulation. It not only tells you the good things, it tells you the bad things. So I think that may save them a few dollars by not implementing some of the ideas they had. The advantage of the simulation, it could show why which projects were good and why which projects didn't make too much difference. Cerro, Colorado and Spence, near each other over in Chile, just looking at fleet management systems there. Olympic Dam expansion project, that was one of my best projects in respect that BHP, this is going to be the biggest mine in the world, and BHP chose TMS as the preferred system to use for that particular project, mainly because it was a lot cheaper than the other projects offerings at the time, but also it was something they could use straight out of the box, so to speak, and it did everything they wanted to do. Corridor Sands, that was about fleet sizing, and Pandora, that was just looking at an expansion to the underground mines there. So that's about it for this introductory video. I hope you got something out of it. This is my logo. The green bit represents the earth, so this bit here represents a profile for an open cut mine, and this represents an underground mine, the decline, so that's where the mine bit is, and the blue bits is the oceans for the port. There's nothing in there about rail. Okay, thank you.